Before quantum mechanics, the laws of physics were thought to be completely deterministic. If I hit this billiard ball, precise measurements of the direction of the force, the shape of the ball, the friction of the surface, and the air currents in the room should be able to tell me exactly where the ball will be at any specified time in the future. This calculation might be difficult, or even completely impractical. But in principle, with precise measurements and Newton's laws of motion, the future ought to be completely predictable. When quantum mechanics came along, everything changed. Uncertainty is an essential property of the quantum world, one that makes quantum mechanics fundamentally different from what we call classical physics. In a game of quantum billiards, we can still make predictions about the future, but those predictions are always going to have some uncertainty built in, even if we start with perfect, complete data. This quantum fuzziness is encapsulated in Heisenberg's uncertainty principle. It says that the more precisely you measure a particle's position, the less precisely you know its momentum, and vice versa. A particle's momentum is its mass times its speed. Essentially, if you know where something is, you can't know perfectly how fast it's moving. One way to think about the uncertainty principle is as a measurement problem. If you're trying to measure anything about a particle, its position, speed, etc., you have to see it first. If the particle isn't emitting its own light, you do that by bouncing light off it. No matter how careful you are, that tiny bit of light gives the particle a tiny bit of energy, and thus changes its momentum. You can try other methods of measurement, but there's no way to measure the properties of a particle without interacting with the particle, which changes the properties of the particle. A more precise way to think about uncertainty, though, is as a consequence of the fact that the particle you're trying to measure is acting like a wave. A wave is, by its nature, not something that can exist at a single point. The simplest kind of wave, like a sine wave, is not localized at all. It stretches out infinitely in each direction. It has a well-defined frequency, which for a wave is related to its momentum, but has no specific position. If you want a wave to have a position, it needs to be a wave packet, a localized disturbance moving through space like an ocean wave, or, for the case of sound waves, a sharp noise. Through combining waves of lots of different frequencies that add together in some places and cancel out in others, it's possible to create a wave packet that only exists in a small region. And you can make that region smaller by adding more and more waves of different frequencies. The more you try to squeeze the position to a single point, the more the momentum spreads out because you're adding more frequencies. The more you narrow in on the position, the more you spread out the momentum, and vice versa. The uncertainty principle isn't saying that we're always uncertain about everything. It's just saying that we can't be particularly certain about more than one thing at a time. Sometimes I picture the wave like it's made of a bunch of bees. Like, you can let them spread out and they'll just hang around being chill, or you can try to contain them all in a small space and they'll be buzzing around furiously. They're not going to calmly fly in formation or collect into a nice stable stack. It's pretty rare for the uncertainty principle to have a practical effect on your life, unless you're doing something like carrying out high-precision measurements with lasers. But the philosophical implications are huge. It means that there's a fundamental limit to how well we can understand the universe and how well we can predict the future.
Throughout history, physicists have focused on precision measurements to try to observe the universe and then use their models to try to build as accurate a picture as we can of the universe. So precision has really been a focus. And quantum uncertainty, though, is teaching us that, in fact, that's not even possible. And that's not necessarily a bad thing. In fact, quantum uncertainty is a powerful idea that actually helps us to expand our thinking about not just the universe, but what we can do with quantum theory itself. For example, how we can use quantum uncertainty as a tool to do a whole new type of computing, which is called quantum computing, or to do even sci-fi sounding things like quantum teleportation.
A world governed by quantum mechanics is not deterministic. No matter how carefully we do our measurements, at some point we're going to have to throw up our hands and say we don't know where the billiard balls will go. Einstein famously hated this idea and hoped to find some way around it. He was quoted as saying, "God does not play dice with the universe." He meant that despite appearances, there cannot be fundamental uncertainty built into the laws of physics. But 100 years later, Heisenberg's uncertainty principle is still here. So, are you feeling lucky?